Logistic Functions brought to you by Angry Pirates of the Caribbean guy. Not sure who he is. So, what I mentioned before with the bacteria, at some point there's a limit to what an environment can support. And so exponential growth, mathematically exponential functions just continue on forever and ever and ever. So their range is positive infinity for all those growth functions. So a limited growth function is more realistic for what happens, say, with populations and other limiting things. So this is, and that type of function is called a logistic function. This is a ceiling, a value that has a limiting value. We call that A, and it's the upper bound. So our population will approach this upper bound. It actually ends up being a horizontal asymptote, but it'll never actually reach it. This is often called an S-curve. So we are going to use Desmos to model what we're told is a logistic function. So apparently bald eagles were near extinction in the US back in the 1960s. So the federal government put it on an endangered species lists, and then they put together all these efforts to protect the eagles. They restored their habitat, got rid of pesticides, like it's illegal to kill them in any way, all kinds of things like that. So we're going to create a scatter plot using these data. Now notice that we're going to look at T being years after 1962. So I'm going to make a T column right here. Note 1962 is not on here. So 1963 would be 1. And then we would do 1974 minus 1962 to get the value that would go here. And that feels like 12. And then if I look at the amount of time between 1974 and 1981, that's 7 years. So this should become a 19. Then we do another 5 years. So this would be a 24. That feels like 16 years. So this would become 40. Another 4 years, that would be 44. We're looking at 6 years after that would be this. And then 5 years after this would be that. Okay, so those are going to be our X values. These are going to be our Y values. Notice the population is actually double this. We're looking at, I think, mating pairs, presumably, because that's the only way you can actually grow your population. So let's switch to Desmos. Oops, there was my Pandora. And we're going to create a table. Notice I hit the plus sign in the left corner and created a table. We're not using X's here. We're using, T's. We're using X1s. So 1, 12, 19, 24. Put in these values. And then put in your Y values. So I'm just typing the number in and hitting enter. Actually, you can't notice that because you can't see my hands, but whatever. It makes it nice and fast to do it. If you're using your cell phone, I'm sorry. That's an awful way to do things, but if that's all you have, I totally understand. I prefer this, by the way, over those ancient TI-89, 84 calculators. So now that I've got my data in there, if I want to get a quick zoom of the scatter plot, I hit this little plus tool in the corner here, and there's my scatter plot. So you can see this exponential growth thing kind of happening here, but then in the last couple of years, it seems to be tapering off, which is why we're going to suspect that this is a logistic function. But let's write out two functions. So we'll put in the exponential one, which is y equals p naught. So we'll call it a times e to the kt. So we're going to do, oops, I forgot to put y1, and we'll do e to the k times x1, and there should be our exponential function. Oh boy, what happened? Did I delete all my data? I most certainly did. There we go. y1 k to the raised to the x1. What is going on here? Let's type in our, I know what, we're not supposed to put the equal sign, we have to put the tilde sign. So let me show you where that tilde sign is. On your key bar under ABCs, here's your tilde sign right next to the enter sign. So y1 tilde AE to the K, and instead of T, we have to put an X1. Okay, so there is our exponential model. Note that R squared value is pretty good, a coefficient determination. Let's now do our logistic model and see if it's any better. So that one was y1 equals a divided by 1 plus, b times e raised to the negative k x1. All right, there is our logistic model. Note that the r squared value is a little bit better. So that is a better function. And let's just zoom out a little bit. Oh, and there you see that S curve. Now, if you think about realistically, the Earth cannot support an unlimited amount of bald eagles. I mean, we're getting up into crazy numbers here, 30,000 pairs here. They're predators, and so it depends on prey. There's all kinds of problems with that. So our logistic model is a little bit better. All right, so let's return back to our questions here. So create a scatter plot of these data. Oh, boy. Desmos did it for us. It was something like this-ish. And then how does it compare to a standard curve? You saw that the exponential one looked like this, and that the logistic one looked like this. So we used the regression, and we graphed the function on top, and it did look like it fit very well. So what appears to be this carrying capacity? Well, if we look at our logistic equation, this A is the carrying capacity, which looks like 29,000 pairs. We could graph Y equals that A value. Let's see, will it let us do that? Nope. We're going to have to type in the number 29083.7, and you can see that that does appear to be that upper horizontal asymptote. So let's go ahead and write down that our A value equals 29,083.7 pairs, bald eagle pairs is what we're looking at. All right, and then finally, we were told that the protection of these bald eagles was to sunset, meaning end all these special protections, when the population reached 7,500 breeding pairs in the lower 48 states. So we're going to use an analytical or algebraic method to predict when this would happen. So that means our P of T is the 7,500, or our Y in this case. And then we had 29,083.7 was our A, and I've got to go switch back to Desmos now to get the rest of the parameters. Here's our K value. So 1 plus, let's see, our B value is at 68.8635. And that's e to the, we should keep really all of these values to be more accurate, 0.571524. Okay, so the question is, how are we going to solve this thing analytically? Well, this is like a mixture of a rational equation, because here's a fraction, and an exponential equation. So let's get rid of the division by multiplying both sides by this. Notice when we do 1 times that side, who cares? So we end up with 7,500 times 1 plus, boy, I don't want to write all this out. I'm just going to write the 68 and e to the negative 0.06, but then I'm going to use these actual numbers when I do the calculations at the very end. I hope you don't mind that. So there's 3 places we rounded. So that's 3 places we've created some error. All right. So instead of distributing this 7,500, I'm going to divide both sides by it. And then I'm going to subtract 1, and then I'll have an exponential thing by itself. So let me rewrite this over here where we have more space. When I divide by 7,500, I'll have 1 plus 68 e to the negative 0.06 equals 29,083.7, which is what the actual number was, divided by 7,500. I will then subtract 1 from that. So I'll have 68e negative 0.06, and this gross thing to minus 1. I'm not going to bother simplifying or calculating any of this. I'm then going to divide all of that by the 68.8635, and then we're almost there. Oops, that should be a 0. divided by, here I'll write in the whole number. Oh, this is getting awful. I'm running out of space. Then, because this is e to some power, oops, I forgot the t in all here, right? So this should be a t here, 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 here. I'm then going to take natural log of both sides, and that'll get us negative 0.06x, or 0.06t equals natural log of this mess, insert that mess. And then the final step to get t by itself is divide both sides by this negative 0.06, not t, 0.06. Okay, that will get us t. Let me rewrite what we're actually going to type into our calculator over here. So our t is going to equal natural log of 29,083.7 over 7,500 minus 1, all of that divided by 68.8635. That's all in parentheses. And then all of that divided by negative 0.0. And now I'm going to input all of this. 571524. All right, we'll switch over to Desmos to calculate this because it's it can handle this nicely for us. So we'll do natural log of 29,083.7 divided by 75. Whoops, I put 100, 7,500, and then minus 1 on that. I'm going to hit the parentheses button and do it one more time. And then within here, oh, fail, that's not what we wanted. I want, I'll go inside here, parentheses in here, divide, here we go, that's what we want, this by 68.8635. I don't need this set of parentheses. I could have left it, doesn't matter. Divided by negative 0.0571,524, and there's our number. It's approximately 55.55 years. So, when did that happen? We would add this number to 1962, and that will get us the year it happened, which turns out to be about 2006. So approximately 2006. Note, this actually did happen in 2007, so our model is pretty good. All right, that's the logistic model. I hope you enjoyed it.